Good afternoon. Today we'll be looking at Calculus Chapter 7-3 volumes. Specifically, we'll be focusing on finding the volume of a solid that you get when you rotate an equation around the x-axis, and we will be using integration. So, like I mentioned before, we will find the volume of a solid when revolving a line around the x-axis. The equation we will be using is volume equals integral of area between A and B. So the volume of a solid of known integral cross-section area from x equals A to x equals B. So this picture here, I hope to help illustrate kind of what will be going on. The line rotation will form a circle. So here's the line. Right here, that's your original function, and when you rotate it, you form an entire solid. This is supposed to be a kind of 3D drawing of it, and when you look at the end, the cross-section, it will form a circle right here. And so the equation line here will equal the circle's radius, and we will integrate the area equation between the designated x values. So for area, we will end up using the formula pi times the y equation squared, which is also if you notice, the equation for a circle because our cross-section is indeed a circle. So we can start by graphing this equation so we kind of get a visual for what it's going to look like. And this is our equation here that we're going to graph, and these are the upper and lower bounds. When we finally integrate it, we'll use those, but they're not really necessary in this graphing portion. So we'll first graph it by putting, this is kind of the point, and then we go up 1 over 3. Oh, that wasn't very accurate. Then up 1 over 3 again, and that will be our line right here. And so when we rotate that around the x-axis, we will end up having one down here too. So then that'll look like that. That will be the bottom portion. And it will actually form like a circle in between those two. So the cross-section is going to look kind of like this, you can see. So then again, this is the y equation will be our radius for the circle. And so now we can start solving the equation. So we will start out using our formula for volume equals the integral between A and B of area of the cross-section and then the d of x that we need there. So, and our area equation again is pi times the equation squared. So we'll put these in. We have the integral between 0 and 6. Area is pi times, and now here we put in the y equation, 1/3 x plus 2 squared, and then we can add the d of x. So we can first off pull the pi out and then rewrite this equation, and now we can solve or simplify that, and we get 1/9 x squared plus 4/3 x plus 4. Now we can find like the antiderivative of that part so we can kind of solve the equation, the integral. So we have the pi times, and this will be 1/27 x to the third plus 2/3 x squared plus 4x. And we are going to solve that between 0 and 6. And 0, since there's x's, there's variables in every one of these, and we're going to be multiplying, the 0 will kind of end up to be 0, you can tell. But the 6, here's the 1/27, 6 cubed plus 2/3 times 6 squared plus 4 times 6. And so there's that. We get pi times the first section equals 8, then the second section equals 24, and this third section equals 24 again. So then that will come out to equal 56 pi. So the volume of this first equation, when you rotate it around the x-axis, will equal 56 pi. Okay, for our second example, we will be using the equation y equals x cubed. So then graphing that, it would look something like this if you put it into your graphing calculator. And then rotating that, this will go down this way, and it does go off this graph a little bit, trying to get to 2. And as you can see again, the cross section will be a circle. So we will use the circle equation. So I'm just going to set this up with all the pieces in it already. So then the lower bound is 0, the upper bound is 2, and we're using the same circle equation. So then we have pi times, well, the radius squared, which in this case is x cubed squared. So we pull out the pi, and we have the integral between 0 and 2, and we can simplify this x cubed squared. That will just equal x to the 6th. I keep forgetting that. And then when we're solving this integral, we get pi times the antiderivative of x to the 6th is 1/7, x to the 7th. So then you solve that in between 0 and 2. So then we get pi times 1/7 times 2 to the 7th. So that would be pi times 1/7 times 128, which equals 128 sevenths pi. And that is, and then, well, 0, that all multiplies out to be 0, so then subtracting 0 will just give you 128 sevenths pi. So that is the answer. And for our third and final example, we will be using the equation y equals the square root of x, which looks tricky, but it's actually really simple. So just kind of bear with me. We'll graph this, and it'll look something kind of like this. And then rotating that around the x-axis, you'll get a interesting little shape there. And then the cross section again will be a circle. So setting up our equation, we have the integral between this states 0 and 4 of pi times circle radius, which in this case is the equation y equals square root of x. So square root of x squared. We can pull out the pi between 0 and 4, and if you know from algebra and stuff that a square root squared is just what's underneath the square root sign, so in this case it is just plain old x. So pretty easy to integrate. So then we solve this, and we get pi, that would be 1/2 x squared is the antiderivative of that. We are solving in between 0 and 4. So we start with, here's the pi, 1/2 times 4 squared. 4 squared is 16, 1/2 of 16 equals 8, so we have pi times 8, which is just equal to 8 pi, because it's typically better to keep things in exact form. And that would be your final answer, so it's a lot easier than it looks. Thank you all for watching, and I hope you've enjoyed this brief presentation. Mr. Plucker wanted us to do something kind of funny, clever for a wrap-up, and I found this joke online, and I thought it was pretty funny, especially since it talks about integrals, so it kind of relates to this topic. There's a big calculus party, and all the functions are invited. Natural log of x is talking to some trig functions when he sees his friend, e of x, sulking in a corner. "What's wrong, e of x?" E of x replies, "I'm so lonely." "Well, you should go integrate yourself into the crowd." E of x looks up and cries, "It won't make a difference."